Hello. There was some discussion on the Hobby Machinist forum about asking about my derivation of this equation to find the taper angle, because a lot of people do it a different way by using the ball height method. So I just thought I'd show the derivation, and actually it's very simple. I just had to think of it just for a little bit. But what you do is, okay, here's the taper of unknown half angle. Here's radius 1, the large radius. Here's radius 2. This radius touches, it's a 90 degree, touches on a tangent, the same here. What you do is you take this line right here and you make a parallel line that is right at the center of the second ball. And what that does is that just makes a right angle triangle right here, 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 here to here. And the height is the center of the ball height. So that's your height. So that's your hypotenuse, is the height. And then the opposite side from the angle theta is equal to R1 minus R2. So you have opposite and adjacent, so that is the sine. So theta is equal to, you see up there, I'll write bigger, inverse sine of opposite R1 minus R2 over the hypotenuse, which is h. That's the crux of the derivation. It is pretty straightforward. Now, to make it one step forward, what I had done is I did it, the equation, so it's from the measured height. So that way you didn't have to figure out where the centers were. I just wanted something you just go in Excel and put a spreadsheet in and put in the variables. So here's height 1, and here's R1, and that is the distance from this line to the center of that ball height. The center of this ball height is equal to, I'm just going to extend this out, R2, so that comes out there, and H2. So this H here, H is equal to H2 plus R2 minus anything above here, H1 minus R1. So that's your H. Plug that into that equation, and you come up with the equation that I used in the Excel spreadsheet. R1 minus R2 over H2 plus R2, which takes you down to here, minus H1 minus R1. And there you go. That's the equation. But anyway, the crux of it is how you measure it. Now, what a lot of other people were doing, actually, and this is a nice clean solution. You can just plug that right into a calculator or Excel. What a lot of other people were doing is a different method for like the ball height calculations. And what they were doing, actually I don't think I need that. We're going to make believe I have a T-square and this is horizontal. What they were doing, let me turn that over so it's down. I'll make these horizontal. And they were solving a triangle. Well, actually this on the horizontal, this distance here, since you have your angle here, which is theta, and your angle here that's theta, the side adjacent is the cosine, so it's R1 cosine theta, and this here to here is R2 2 cosine theta. Because whenever you have a triangle, and this is r, this side adjacent is always r cosine theta, and this side opposite is always r sine theta. I find that a lot easier than doing a geometric solution with the Pythagorean theorem, because it's just you write it down, boom. You don't have to figure out anything else. You have the radius, you just do that, it's r cosine theta. So, okay, so, but anyway, usually they'll do this to figure out this h, which is measured differently here to here. That h is not measured from the ball height like mine. It is measured from the level where these two planes touch the wall. And so what they do is they'll project this over here now. This is a method. And very similar to mine, where I did R1 and R2, with this distance here, here's your triangle, here to here to here to back to there. With this distance here on this triangle, I'll draw, what this distance right here is R1 cosine theta minus this distance over here, which is R2 cosine theta. And then they do it over this h here. And it's the inverse. Let's see, you have opposite versus adjacent. That would be tangent. So the problem with this is it requires an iterative solution. There's no direct solution to this. Now, an iterative process I describe to people as the guess a number game. If I tell you that I'm guessing of a number and you got to guess what it is, and it's between 1 and 100, most people are going to start at 50, and if I say higher, they go to 75. If I say lower, they go to like 62 or something, and then just go through that process. That is an iterative process. And the way to solve this using an iterative process, and there are processes, but in effect what you're going to do is you're going to put in an angle that you think it is, run the solution, and see if this one comes out the same. And based on the answer, you can make it higher or lower and work your way into it. And there's ways to do it even more efficiently than just guessing, but it's still a guessing game. Excel does iterative solutions. So if you had this equation, and there are people that have on the forum there, they would put it in with an iterative solution, and it would do it. That's an option in Excel where you can actually solve something like this. Me personally, this is where I started. When I first came up with a solution, I came up with something like this. But I figured it could be solved, in a direct form. So I just looked at it at a different angle and brought this in over here, and it's a really direct solution. So give it a try. I have an Excel spreadsheet, and it's actually on a thread. I found one place to put it. If you go to the Hobby Machinist in the general questions and answers, I have a 2-pole taper measurement question thread, and I was able to upload it to there. So there is a copy sitting there. The angle is given and calculated in all the calculations in degrees. If you were to move the graphic, I actually have the radians calculation under there, which goes into some of the calculations. So I just kind of like hit it there, not to confuse people. But anyway, that's the derivation of the equation. Real straightforward, so simple it's funny. I hope you enjoyed this, and I hope it helped clear up what I did. Thank you. Bye.